Hey everyone, Terry here, and we're going to calculate the entropy change for the mixing of two ideal gases. And this is what's going on. We have a container, and in that container is a divider, and on one side of the divider is one gas, and the other side of the divider has another gas here. When we remove this divider, this gas is going to mix into the whole area, and same as the other gas here. And we saw in the last video that when a gas expands like this, we have a change in entropy, and the change in entropy increases. It's greater than zero. And this is the equation that we derived in the last video here. And I'm not going to derive this for you. We're just going to kind of use this equation. But what's happening is, imagine we have no red gas. There's only blue gas here. And if you remove the divider, there's only blue gas. This blue gas is going to expand into this empty area and take over the whole volume. Well, when it expands, it's not pushing on a piston. It's not performing any work. So it's not losing any energy. It's not losing any kinetic energy. And we don't have any heat transfer from the surroundings here. So this is an adiabatic process. There's no heat transfer. And because there's no energy loss due to work, the gas is at the same temperature afterwards and before. So it's isothermal. And it's an irreversible process because it's extremely unlikely that once you remove the divider and the gas expands, that the gas will come back all to the one side of the container. That's just not going to happen. So it's an irreversible process. To get the change in entropy of both gases mixing, we literally calculate the change in entropy of the first gas expanding. Imagine that it's expanding by itself with no red gas here. And we add that to the change in entropy of the other gas. Imagine that's expanding by itself. And we can ignore the other gas when we calculate the change in entropy for each one because these gases are ideal. And that means they experience no intermolecular forces. They experience no interactions with each other. They're just expanding and ignoring the other gas completely. So we just sum them all up. So we're going to use this equation into each one here. And this is what we get here. We have the moles of gas A times R times ln of the final volume, which is the sum of the volume of each container here. This is the volume A, this is volume B, so the sum of them is the total volume divided by the volume that it's in, so the initial volume. And then the same thing for B here, the moles of B times R times ln of the final volume, it's the final volume, just sum them up, divided by the volume that the B is originally in here. At this point, we can literally plug in our numbers. I did that for you to save some time. So if we have, say, 9 moles on the left-hand side, and I got that by counting these balls, 1, 2, 3, 4, 5, 6, 7, 8, 9. I know these are molecules, but just pretend they're moles. So that's 9 moles. And then on the right-hand side, we have 1, 2, 3, 4, 5, 6, 7. So we have 9 moles on the one, and times the gas constant R 3.145 joules per mole Kelvin, and then ln of the volume. So the final volume is 1.0 decimeters cubed plus 0.8 decimeters cubed divided by 1.0 decimeters cubed. And then plus, we got to add this other term, which I got right here. This is 7 moles for the other gas plus R, and then plus ln of the final volume over its initial volume there. And if we plug that into the calculator, we get 91 joules per Kelvin. So that's a positive change in entropy. They're expanding. The change in entropy of the surroundings is going to be 0 because there's no heat transfer with the surroundings. So this will also be the total change in entropy for the universe as well. All right. Hope you liked it. See you in the next video. Cheers.